So we're going to learn about something called alternating series now. Alternating series means that the sign alternates from positive to negative to positive to negative to positive to negative, back and forth, back and forth. And the key way to make a series alternate is by including a -1 raised to the n if we wanted to start with a negative term, or -1 raised to the n plus 1 if we wanted to start with a positive term. Doesn't really make a difference how we deal with them. Doesn't matter whether we start with a positive or a negative. We deal with them the same way. Okay. The idea behind these is we keep on bouncing back and forth, but getting closer and closer and closer to a converging value, if in fact it does converge. So the alternating series test always comes in two parts. You have to do both parts to use the alternating series test. So the first part is we have to look at not the alternating terms, but just the absolute value of the term. So that's just the a sub n. A sub n is going to always be positive, and then the alternating part is kind of factored out. We have to look at the limit of these terms and make sure that those approach 0. Not only that, but we have to say that for all values of n, the next term is smaller than or equal to the previous term. The n plus first term is the term that follows the nth term. So we have to see this continually decreasing sequence of values in order for this to work. Okay, so again, we have to show each of these two different pieces in order to use the alternating series tests. This is never going to be a test for divergence. We can never say that an alternating series diverges by the AST. This is only a test for convergence. So if this part fails right here, then we've seen that before, right? We've seen that as the nth term test, right? If the limit does not equal 0, then we just stop and say this series diverges by the nth term test. So yeah, basically we recognize that each one of these is an alternating series because we see that -1 raised to the n. We'll talk about C in a moment. But once we recognize it as an alternating series, then we ignore the alternating part and we just do these two tests. And if it passes both of these two tests, then the alternating series converges. All right, so start off with example 1a. We're going to look at the absolute value of each term. That's going to be n over 2n minus 1. Well, the limit, this is the first part of the alternating series test, the limit as n approaches infinity of n over 2n minus 1 equals 1/2. And the most important thing about that is it is not equal to 0. So we don't have to do anything else. We can say, therefore, the series diverges.
I didn't get that. Could you try again?
By nth term test. I should just turn off my phone when I'm talking about these. All right, so we don't use the alternating series test because it fails the nth term test. All right, cool. So move on to the next one. Again, ignoring the alternating piece of this, we're going to look at the limit as n approaches infinity of just the n over the natural log of 2n. Now, if we recall our hierarchy of infinities, this linear progression grows faster than this natural log. So that means that the numerator is bigger than the denominator, so this is an infinite limit. This fraction grows without bound, but whatever it is, it's not equal to 0. Therefore, this series also diverges by the nth term test. Okay? So, what about this one? I don't see a -1 raised to the n. But let's remember, when in doubt, expand it out. If we let n equal 1, we're going to take the cosine of 1 pi over 1. If we let n equal 2, we're going to take the cosine of 2 pi over 2. And if we let n equal 3, we get cosine of 3 pi over 3, etc. And when we evaluate these, we should recognize, wait a second, cosine of pi is -1, and cosine of 2 pi is +1, and cosine of 3 pi is -1. And we actually have an alternating series in disguise. In fact, we could rewrite this in a more friendly form as -1 raised to the n over n, right? Because when n equals 1, our numerator is -1. When n equals 2, our numerator is +1, etc. This looks familiar, right? This is almost the simple harmonic series. This is, in fact, the alternating harmonic series. So instead of adding up the reciprocals of all of the positive integers, we are alternating between adding and subtracting. So remember that the alternating series, the simple harmonic series diverged by the p-series test, or the integral test. But if we start subtracting half of the terms away from this, maybe that's going to make this thing converge. So let's take a look. This is going to be a two-step process, right? We're going to take, first of all, we're going to take the limit as n approaches infinity of 1 over n. Clearly that's going to equal 0. So we put a little check next to that. The next question is, do these terms progressively get smaller? Is it true that a sub n plus 1 is less than or possibly equal to a sub n? So we'll go ahead and write that out by writing 1 over n plus 1 less than or equal to 1 over n. Okay? Now we're going to ask, is this a true statement? You can justify this being a true statement by saying, oh, well, n is positive, first of all. So when we add 1, that denominator gets farther away from 0, which makes this fraction closer to 0. So since we've got a positive value that's closer to 0 than this positive value, then yeah, that's going to be true. You can kind of reason your way through it. You could do some algebra to prove this as well, but normally if you feel this is a fairly obvious statement, then we'll go ahead and say, yeah, sure, we can accept that. That looks like a true statement to me, so I can verify that. If it's not immediately obvious, then maybe you would want to do some algebra. Anyway, because this series passes the two tests, the two parts of this one test, then we would say, therefore, the series converges by the alternating series tests. All right, so this is an example where if all of these were positive, then it would definitely diverge. We've talked about that one at great length. But this is now because we take half of the terms and made them negative, and then when we add that up, we actually get a finite value. So there is our first converging alternating series.